Log on, tune in, find out. Another good idea from Cambridge.
So any questions, I guess, that I should just first ask? Unfortunately, I don't have time to talk about that. All right, so there are two things I will try to cover a little bit. So when you do this for the general L values, you get a set of vector values Mach modular forms. And then secondly, you can compute, or try to compute, and understand analogs of the McKay-Thompson series for G, an element of these groups, where you replace the dimension of the representation by some character evaluated in that representation.
Does vector values here just mean that you've got several of them for each?
So let's first talk about modular forms. So a vector valued modular form would be, I don't know what I should use for calling them, but I don't know, psi, let's say. Psi r equals 1 to n, would be functions of tau that under a modular transformation goes to some rho sum on S, rho rs, all right, psi r goes to some sum on S, rho rs, psi s, where the rhos are a representation of SL2Z. So in other words, for each, I just need to do it for T and S, the two generators, there's some n by n matrix. And those matrices form a representation of SL2Z, and the modular, vector valued modular forms transform their tau argument by a modular transformation, but then also have a matrix that acts on this vector and transforms it as well. So that's a vector valued modular form.
They're all with the same weight.
All with the same weight. And things like this occur in string theory all the time. For example, if you have a rational conformal field theory with some n blocks, and you ask how do those things transform under modular transformations, they generally transform as a vector with some explicit matrices that tell you how the different blocks mix into each other.
So that was the case for the two you wrote down, Prev equals 3.
Yeah. Now I haven't told you about a Mach modular form yet, but that's what a vector valued modular form would be.
So these rows can depend on the weight explicit, I mean factors like C tau plus D.
No, so well, they depend on, for each element of SL2Z, you get some matrix which represents it. So yeah, I mean, they depend on the element of SL2Z.
Right, but for a single modular form, you have C tau plus D to some power K.
Right. Yeah, so each of these has the same weight. Each of the components has the same weight. And then they transform as a modular form, so there's some...
Oh, I see. The factors in front as well as this linear combination. Right.
So for each element of SL2Z, I get some n by n matrix, and so I have to choose a So I choose a representation of SL2Z, some n-dimensional representation. Okay, so mock modular forms. I will start by telling you about a particular kind of mock modular form, which are mock theta functions. And I can't resist, in case you don't know it, just saying a few words about the history, because it's so tragic and romantic and interesting. So, as I'm sure you know, Ramanujan wrote to Harvey. I mean, he did these amazing things. He wrote to Harvey. Harvey, after several mathematicians ignored his letters as a crank, Harvey thought he had done brilliant things, invited him to Cambridge, and he spent 4 or 5 years in Cambridge, and then went back to India. And somebody said he actually died, not in India, but back here in Cambridge where he came for treatment. But anyway, a year after he left Cambridge to go back to India, he died of something.
In India,
That's what I thought, but anyway. So during the last year of his life, he had, a set of papers, a notebook that he was working on. And he wrote a letter to Harvey from India in 1920, and in that letter, he proposed to study what we would now call mock theta functions. And he wrote them down, and I'll give you an example of one of them. And he labeled them by an order, but he didn't define what the order was. He just said this was an order 3 mock theta function. And I think the mock might have been inspired by the mock turtle in Alice in Wonderland, because it was somehow not quite, it was like a theta function, but not quite legitimate. So the notebook that he was working on, which is really just a collection of loose leaf papers, was sent by his widow to Cambridge, to Harvey. And Harvey had them in his papers, and before he died, he passed them on to Watson. Watson then died, and apparently his papers were a huge mess, and there's just a pile of train schedules and mathematical notebooks and scribblings and junk. And it was about to be incinerated, but Whittaker, I guess, and Rankin went through it and spotted these papers from Ramanujan. So they pulled them out, and they sent them to the Wren Library. And by that point, the mathematical world really lost track of the fact that they ever existed. And then George Andrews in 1968 was in Cambridge and wanted to know about something related to modular forms. And so he said, I think there might be something in the papers of Watson, which you can find in the Wren Library. So he went, he dug through these papers, and he came up with these sheets of paper that were Ramanujan's work. And so in the mathematical literature, this is sort of compared to somebody finding, a 10th symphony of Beethoven or something. The mathematical world was completely unaware that this existed. And this lost notebook contained a lot of new mock theta functions, as well as various identities that they obeyed, which people had not known about. So that revitalized interest in them. And you can go over to the Wren Library and you can see these. I mean, Julian Soner arranged for me to go over there, and it's, there's a box, and in that box there are 87 pages of loose leaf papers written by Ramanujan, and it's really kind of fun to go look at them. Anyway, the somewhat more modern understanding actually only dates back to 2002, when Zonder Swagers, who was a graduate student of Zagier, kind of realized that a lot of the old work on them, which is very impenetrable, could be put in a nicer setting. So the understanding is really about 10 years old, and they seem to arise now in string theory in various ways. Black hole counting, moonshiny things. We heard a seminar from Jan Maschot about how they show up in the computation of calculations of n equals 4 Yang mills on various surfaces. So they're an interesting subject. So here's an example from Ramanujan's original paper. I think this is the first one he wrote down. And he wrote it down just as a series in Q. Right, so the pattern is clear. You have the squares of integers on the top, and then increasing powers of 1 plus q to the n quantity squared. And this is what it looks like. So let's call that the sum of a m q to the m. Now, these things have lots of interesting properties. One thing that they have, which is not going to play any direct role, but I think it's worth mentioning because it's kind of suggestive, is that there's a combinatoric interpretation of what these coefficients are. So you know if I take 1 over the product of n, 1 minus q to the n, that I can write that as a sum on m, p of m q to the m, where this counts the number of partitions of the integer m. So Freeman-Dyson, in trying to understand various things about work of Ramanujan, thought that there was might be a combinatoric interpretation of some of what he had done. And so Dyson defined the rank of a partition of an integer to be the largest part minus the number of parts. So for example, 4 has a partition where it's written as 1 plus 1 plus 2, and the rank of 4 is its largest part, which is 2, minus the number of parts, which is 3, which is minus 1. So it turns out that A of m, appearing in the expansion of this third order Mach theta function of Ramanujan, is the number of partitions of m with even rank minus the number with odd rank. So properties of these things are of interest to number theorists and people that do combinatorial sort of identities. But for what we're going to do, it's more interesting to know that Mach theta functions have two kind of hidden invariants or properties associated to them. So one of these is a rational number, and the second is something called a shadow, g of tau, which is a holomorphic weight 3/2 theta series in one variable. And I'll give you some examples of such theta series in a minute. So what do I mean by it has these hidden invariants? Well,
So the thing that you wrote is not supposed to be quite modular, right?
So that's exactly what I'm going to say now. So f of q, which is the Mach theta function, is not modular. But it is holomorphic. On the other hand, there's a guy f hat of q, which is some rational power of q times f of q, plus or minus something I'll call g tilde of q, and there's some factors here which are not so important, but the basic idea is This guy is not holomorphic, but if I take d by d tau bar of it, that vanishes on this, which is holomorphic. But this guy is not holomorphic.
So, as it was a function of Q, it's Q bar as well.
Yeah,
Okay.
not holomorphic. And its derivative with respect to tau bar is up to some factor, the complex conjugate of this shadow, which is a holomorphic weight 3/2 theta function. So this is not, this is not completely transparent what's going on here. It sounds rather complicated.
Hold on, sorry.
But
Does it mean that Q tilde or G tilde is anti-holomorphic? Or not?
no, it's not holomorphic or anti-holomorphic.
Because
But
the relation you wrote there seems to be only dependent on theta bar.
no, but G tilde could have some tau dependence in it. D by d tau bar would kill that. But it's like a holomorphic anomaly that we talk about in supersymmetric theories, in that there's a holomorphic object, but it doesn't transform the way you would like. And then there's a non-holomorphic object, which does transform the way you like, but it's not holomorphic. There are a lot of other things about these guys, but this is sort of the basic definition. You can generalize this. So here we had, and I should also say that f hat of q has weight 1/2 under modular transformations. So you would say f of q is a weight 1/2 Mach modular form. And you can generalize this property of weight 1/2 and 3/2 of the shadow and the completion of this guy to weight k and k minus k and 2 minus k. And if you generalize it to this pair of weights, then these things are just called Mach modular forms. So Mach theta functions are a particular subclass of Mach modular forms.
So is it the F or the F hat which is called?
F is called the Mach modular form. F hat is called its completion. G of tau is called its shadow. And this thing is sometimes called its Eichler integral. Because if I integrate this equation to get G tilde, then I write G tilde as an integral of G of tau. So that's the terminology.
Since you have to choose alpha as well as G tilde for a completion, so is there a unique completion, or could there be many ways to choose?
I think there's a unique completion, but I don't know if there's a theorem to that effect. In all the cases I know, there's a unique answer.
Will you tell us what alpha and G are for the
Yeah.
theta?
So I'll give you I want to give you one reference. There, are these Bourbaki seminars where various mathematicians explain to other mathematicians some new development. And Zagier's Bourbaki seminar on Mach modular forms is not too bad to read. For the K3 M24 story, the quantity I called H21 of tau is a Mach theta function or at least a rational power, that rational power times a Mach theta function, with shadow 24 eta of tau cubed.
So are you going to prove that? Or
No, I'm not going to prove
how
it.
do you know that?
What?
How do you know that?
Because people smarter than me,
When you
smart,
didn't know anything about it, you go down the series without knowing why you're looking down.
right. So you have to use, I mean, there are two ways of doing it. One is you use the known modular transformation properties of characters of n equals 4, which you have an answer written in terms of. Or there's another way, which I'm not going to talk about, but is partly in Zweger's PhD thesis and has, I think, a clearer explanation in a paper by Dabelkar, Murthy, and Zagier, which is hopefully coming out soon, but has been in preparation for a couple of years. And they have a method where you start with meromorphic Jacobi forms that have poles and extract from that a kind of polar part, and then you're left with something which has an expansion in Mach modular forms, and you can use transformations of Jacobi forms to prove the Mach modularity of the things you get. And you can extract this guy from their procedure as well as from doing it without ever mentioning n equals 4. So there are various ways, but I don't know any two-line way of proving this. Sorry. I can mention, though, that eta cubed can be written as S21, where SMR is sum on n 2mn plus r q to the 2mn plus r squared over 4m. And this is a weight 3/2 theta series. That's fairly standard. You can think of it as really the derivative with respect to tau, up to some factor, of an ordinary theta series, which has weight 1/2. And so eta cubed happens to be S21, and so this shadow actually is a weight 3/2 theta series, even though I've written it as eta cubed. And it turns out that these SMRs, where r goes from 1 to m minus 1, are the things that are involved as shadows for the Mach theta functions we get for these other values of L, not just the K3 M24 story. Okay, so let me also, so these guys also come up when you study McKay-Thompson series. So remember in the monster case, what we did was we replaced, so we had this presumed set of vector spaces. And if I put G equal to the identity, then I just get the dimensions, and that's J of tau. So T1 of tau is J of tau with no constant terms, so minus 7044 in some convention. And we then replace the trace of 1 by the trace of G for some group element. We can do the same thing with these Mach modular forms, because there we also have a set of Mach modular forms that we can twist by G. So if I well, I don't know, I think the answer, I mean, the idea is clear enough. So I guess, so for H21 of tau, for example, I had 2q to the minus 1/8. This was the rational power that I had to multiply by. Then I had minus 1 plus 45 q plus 231 q squared plus dot, dot, dot. So if I want H21 twisted by some element g, this is just the identity, but then I have the trace of g in the 45-dimensional representation times q plus the trace of g in the 231 q squared plus dot, dot, dot. So I can get these Mackay-Thompson series for each of these Mach modular forms that appear. Now, in the case of the monster, or here, we sort of know what we expect, because if I just think of conformal field theory, I mean, these aren't really corresponding to conformal field theories, but I can just use that intuition to figure out the modular transformation. So I know that if I take, so inserting G is like putting a G boundary condition in the in the time direction, in the torus amplitude. And if I ask which elements of SL2Z preserve that boundary condition under modular transformations, the answer turns out to be gamma naught of Ng, where Ng is the order of G, and gamma naught Ng are the elements of SL2Z with C congruent to 0 mod Ng. And you figure that out just by, looking at, how this transforms, and then checking that if this condition is satisfied, that you preserve the boundary condition. So that suggests that what we really expect is that these guys should be vector valued Mach modular forms for gamma naught Ng. And again, vector valued now means that I have to choose some Ng dimensional representation of SL2Z, and they transform like a Mach modular form, but with a matrix. So again,
What are the components of that vector?
So the components here are labeled by M. M goes from 1 up to L minus 1. And I had these special values of L. So for each of them, the Mach modular forms are really vector valued, and the vectors have L minus 1 components.
And they mix up under...
And they mix under modular transformations. And these Thompson series are going to mix not under the full modular group, but you expect them to mix in themselves only under some congruent subgroup, which is this gamma naught of Ng. So, there are, however, a lot of subtleties with this. So, and I don't want to get into too many details, but I just want to say a few things. So TG, which was what we were doing in the monster case, or this guy, might turn out to be invariant under a larger subgroup. And in the monster case, the fact that it turns out to be invariant under a larger subgroup is actually important in this genus 0 property. There can be phases, which you can think of as a 1D representation of the transformation. That is for L equals 2, where there's only one M value, You still get phases in the modular transformation law, so it has the same structure that you have to choose a representation of the modular group, but the representation is one-dimensional, or for L greater than 2, L minus 1 by L minus 1 matrices. So you have to deal with that. And, well, anyway, so it's a little bit complicated. But I'll just tell you, I don't want to spend too much time because I think we've had enough, but I just want to mention 2 examples of the kind of results that we find. All right, so let me mention one thing. So the case that we really understand the best, other than the K3M24 story, is L equals 3. The group here is 2.M12. And this guy that I called phi 3 has a decomposition into n equals 4 representations. And these led to the guys that I called H3, 1 of tau, and H3, 2 of tau that I wrote down before lunch. Now, just so in the K3M24 guy, this number is 24. And that was important because M24 has a 24-dimensional permutation representation, which in terms of irreducibles is actually 23 plus 1. But that's standard when you permute n objects. There's one linear combination that's invariant and then n minus 1 that transform irreducibly. So now we have 12, and M12 has a 12-dimensional permutation representation, which is 1 plus 11, but 2.M12 has a 12-dimensional signed permutation representation, which is irreducible by itself. So if you want to compute Thompson series, you have to figure out whether 12 is 12 or 1 plus 11. And it matters. And it turns out that things fall into 2 classes. So define chi1 of G to be the trace of your group element in the 1 plus 11, and chi2 of G to be the trace of G in this 12-dimensional representation. So if chi1 of G and chi2 of G are both equal to 0, then it turns out that the coefficient of the shadow vanishes, and you get ordinary modular forms for the twisted Thompson series. And just as an example, if I look at this guy, there turns out to be a conjugacy class of order 4 elements, and this is what the Thompson series is as a ratio of eta functions. Now, when I say that's what it is, of course, this comes with a certain amount of waffling, because what do we actually have? We have some Q series. We identify the coefficients with representations. It becomes hard to do that uniquely after a while. You then do it as high up as you can. You then compute these twisted guys. You then have to try to match this onto some thing that has the right modular properties, but we're able to do that. The other class has either chi1 or chi2 not equal to 0. And I'll give you an example here, and then I'll stop. So there's a conjugacy class of order 2 elements. And we find by matching the Q expansions up to order 10th that the Thomson series is precisely Ramanujan's Mach theta function. And as a matter of fact, there are 26 conjugacy classes. And so since we have H13 and H23, we get 52 different Mackay-Thomson series. And we can identify all of them either with ratios of eta products or with various combinations of the order 3 Mach theta functions that Ramanujan wrote down. I have no idea why Ramanujan wrote these things down, and they're now showing up as Mackay-Thomson series associated with groups, but they are. And it's quite remarkable that you can look at the expansions of these things and then do these computations and match them up, bang, bang, bang. The coefficients just come out exactly right. So
maybe you said this, but did Ramanujan define only one, this function?
no, he defined seven different order 3 Mach theta functions and maybe 4 or so Mach order 5. And then in his lost notebook, he had some more of order 10 and some more of different orders. It turns out, so he never defined the order. But the Mach theta functions that occur in all these Mackay-Thomson series are order 3, according to his definition of what the order was. And they all show up at L equals 3. Now, for some other values of L, we can also identify some of them with Mach theta functions, but the order doesn't always match L, but it seems to match when L is prime. So anyway, so I mean, it just looks rather magical, and it's not understood what's going on, but I think it is a sign that the K3M24 story, if not the tip of, I don't know, how much of an iceberg is underwater? How much? I don't know.
Like 8/9 tons, something like that.
8/9?
Yeah, I guess.
Well, so we have 6 examples, so it's sort of like a tip of iceberg. I mean, the K3M24 seems to be 1 out of 6. So 5/6 is underwater, but we're hoping to...
So why is it 1 out of 6?
Well, because we have 6 examples, and K3M24 is just one of them. So the K3M24 is kind of the tip of the iceberg in that it's part of a much larger story of groups, Jacobi forms, Mach theta functions, and all sorts of weird identities that we don't really have an understanding for yet, but can be discovered experimentally. So I think I'm just going to stop because you're probably tired. I'm tired. It's kind of warm in here, and so I'm happy to answer questions, but I think I'll not lecture anymore.
Questions?
So any intuition where the bottom of the iceberg can come up in physics?
Well, I think one obvious possibility is CHL models, as Sunil mentioned. So those also have n equals 4, but they involve starting with K3 times T2 and then twisting by some Zn. The hint of that involves something I really didn't talk about, but involves the fact that these Jacobi forms have lifts to Siegel forms, and those Siegel forms are showed up in the counting of Dion states in those theories. I think there is also some hints of some structure like this in threshold corrections in n equals 2 theories, just from perturbative calculations of the form that many people did, including me and Greg Moore. If you choose the right kind of compactification, so you have a number of vector multiplets, so that the vector multiplet moduli space looks like a Siegel upper half plane, and so, you know. There are some connections, it seems, to K K3 surfaces that are elliptic fibrations, but I don't really know why, because, I mean, the elliptic genus doesn't depend on what kind of a K3 you have, but the groups we have here have special properties and could be associated with Dinkin diagrams, and the Dinkin diagram, which I haven't talked about, and those Dinkin diagrams have to do with classifying certain kinds of singular fibers in elliptically fibered K3 surfaces. And again, I don't know why, but that's kind of a hint of a connection. So I don't know. There are a lot of different hints, but nothing that is obvious. I guess we're writing up a paper on the math part of it, and then we would like to think about exploring the physics or string theory interpretation in more detail, but we don't have any one compelling idea as to what is going on. But there's certainly hints of connections to things in string theory.
Could you have a comment on this kind of 2D CFT story and pure chance simons in ADS 3 by mentioned by Witten's paper in 2007? Do you have some comments?
I'm not sure what the question is.
Okay.
Or what's the relationship to?
To the pure chance in the context of the ADS CFT correspondence.
Mhm.
This CFT2 corresponds to some pure ADS gravity in
Right.
ADS3, which is written in the pure chance simons form.
Oh, you mean the monster, his conjecture that the monster.
Yeah.
I'm very skeptical about that.
Skeptical.
Yeah, I mean, I think, I don't know. There were several papers by a number of people, which I think cast some doubt on that general idea. But independently of those papers, I mean, I can just tell you why I'm kind of skeptical. Because in the monster theory, there are 196884 dimension 2 operators in the conformal field theory. That's that coefficient 196884. Those are dimension 02 operators. Now, in the ADS CFT correspondence, dimension 2 operators correspond to massless spin 2 fields. If I have one of those, 102 operator, which is the stress tensor, the dual field in ADS3 is the graviton. And so it makes perfect sense that I could, use that duality and compute things starting with gravity in ADS3 in conformal field theories where that's the only dimension 2 operator. But if I have a theory with 196884 dimension 2 operators, I would expect that the dual theory is a theory that has 196884 massless spin 2 fields. And that doesn't look like Einstein gravity. I don't know what it is. It maybe is something like one of these higher spin theories, but it said it has multiple spin 2 theories. I think Witten somehow hoped that the other 196883 were going to come out of the theory by some magic. But I find it very remarkable that you would, I think you have to start with some of the structure of the monster in the ADS3 in order to get that structure out. I don't think the whole monster symmetry is just going to come out of thin air. So if there is an ADS3 dual, my own feeling, which could be wrong, is that we don't know what the starting point is. It might be some generalization of gravity that has ADS3 as a solution, but I find it hard to believe that it's just plain Einstein gravity.
Yeah, just relatedly, I mean, couldn't you have these different number of the spin two particles as different ways? Say SL2 is I mean it's embedded under I mean in this bigger group.
Yeah, I don't, yeah. I mean, you need something, I think,
Yeah.
other than just pure gravity, but
Because I mean, just speaking about the higher spin theories, say if you have an SL3,
Right.
there are two different ways in which you could embed your SL2 in it.
Uh-huh.
And as you go up, I mean, this is bound to increase a lot.
Right.
Was n equals 4 really, do you feel that n equals 4 was totally crucial for this whole structure, or do you think there might be a version of it?
Well, there is in this paper by Dabokar, Murthy, and Zagier, there is a means of obtaining these guys which doesn't explicitly mention n equals 4. But if you look at the actual formula that they involve things like, well, so they have Jacobi forms that have poles in the variable z. They then isolate that pole and they kind of average it over the elliptic curve so that you get something that has elliptic transformation properties. Then they subtract that and they're left with something else. Well, if you look at the actual formulas, the thing they're subtracting is a massless character of n equals 4. I mean, that's the function that they define, even though they define it in some way which doesn't mention n equals 4. And the thing they're left over with has a decomposition into massive n equals 4 characters. So, yeah, it's not really completely clear to me whether n equals 4 is crucial or not.
So yesterday you sort of indicated that the monstrous moonshine thing really reached not the end, but maybe its culmination in the work of Frenkel, Lebowski, and Merman, who constructed the monster
Right.
group using vertex operators. Is there something analogous we should look forward to here? And if so, what do you think it is?
There's something you should look forward to, but well, I'd say there's something you should, if you're interested in this, there's something people should be working on, which is to find what that is. I don't know what it is. I mean, if I knew, I would tell you.
Goal, because in this case, I assume that, so in that case, the idea was the monster group is such a big group and we don't know what it looks like, and now with vertex operators, somehow we construct it. But these are Matthew groups, they're much smaller, right? So it's
But I don't think the motivation there was to learn more about the monster. I think the motivation there was to understand the connection between the monster and modular functions, which seemed like it was such a completely different mathematical
So in
topic.
that case, just constructing vertex operators for the Matthew group could be an exercise that...
Yeah, but I think it's a challenge to do. Well, I don't think just a K3 conformal field theory is quite the right framework, because I doubt very much that there is any K3 conformal field theory that has M24 as a symmetry. So you have to first figure out some kind of algebraic structure that isolates the BPS states. Well, we know things like that, but nobody's really shown that you can define it carefully in that M24 acts. Or it might be you need something more. Maybe it's really not a symmetry. Well, I don't know. It might be a symmetry of something bigger, including non-perturbative states, but then you say, well, then why is it there in the elliptic genus? I don't know. You may have to take K3 and add something else onto it, or twist it in some subtle way. Yeah, I think it's a great question. I'm sure it has an answer. I mean, I'm relatively sure it has an answer, but I don't think we know what it is yet. So I think that's one of the really interesting, outstanding questions in this area.
Okay, so I think on behalf of everyone, I'd like to thank Jeff for this wonderful series.